So in this video, we're going to walk through a hypothesis test for a mean from one population. And we just looked at an example in the previous slide for a hypothesis test for a mean, but we'll see that this one's going to be a little bit different. So here, the idea is, are sleeping patterns for students at CU Denver any different from, say, sleeping patterns of adults in general? And so here what the researchers are trying to gather some evidence for is that are the sleeping patterns of students at CU Denver different from what is recommended amount of sleep for all adults, which is this 8 hours of sleep. So if we're setting up our hypotheses, we've got the null, the alternative. These are claims about a mean, so our notation that we would want to use is mu, and we would always use an equality in the null hypothesis and some inequality in the alternative. And since the idea here is that they're just trying to see whether the sleeping patterns are different from the recommended 8 hours for the population, as opposed to saying, are the CU Denver students getting more than the recommended or less than the recommended? So the fact that we see is this different is telling us we're going to use a not equal to sign in the alternative hypothesis. And the population mean that's claimed is 8 hours. So these would be our hypotheses. And let me just say that if we were to try and state this in words, here what we are saying is that CU Denver students get the same amount of sleep. And the alternative would be that the CU Denver students are different from the recommended sleep. So I would suggest that you guys practice explaining these hypotheses both in terms of the notation, because that's going to be helpful when we actually do the mathematics, and in terms of words in practical terms. That's going to be helpful when you try and explain these results to someone who does not have as much technical training in this as you do. Okay, and so what's important here, hopefully you've noted that because we have this not equal to sign, that this is going to be a two-tailed test. Okay, so now we want to calculate the test statistic and interpret its meaning. And again, the test statistic is going to give us a measurement of how extreme is our sample. How far away is our sample from the claim in the null hypothesis? So the simplest way to do that would be to say here was our sample mean, and here was the claim in the null hypothesis. But again, just looking at an absolute difference really doesn't tell us much, because we should expect that these are not going to be exactly equal to each other. So what we'd like to know is this difference, relatively speaking, big? And when we say relative, that means relative to the error that we should expect in the sampling process. And the error that we should expect in the sampling process is measured with the standard error of the sampling distribution. And here's where we have a distinction in this example and the prior one, and that in the previous example we had some information about the population standard deviation. In this example, we don't know what the standard deviation is for the amount of sleep of the population. But what we do know is what the standard deviation is from our sample. So instead of using a normal distribution, when we don't know what the population standard deviation is, then we use the standard deviation from the sample instead. But keep in mind, when we make that change, we get a different underlying distribution. We no longer have a normal distribution describing our sample to distribution of sample statistics. We now have a t-distribution. So when we ultimately calculate the p-value, we want to be sure we use the correct distribution, which in this case would be a t-distribution. But now we've got our mean from our sample was 7.5. The claim was that it should be 8. And our standard deviation from our sample was 1.7. And here we have a total sample size of 22 students. And we might have some reservations about actually using a t-distribution with this small of a sample. And so one thing that should have been given in this problem would be that we can assume that this is being pulled from a population where the distribution of sleep times is approximately symmetric. And if that's true, then this will approximately follow the t-distribution. And so if we calculate this test statistic, this comes out to a negative value. So it's a minus 1.3. And I'll round this off to 2 decimal places. So it's about minus 1.38. And so now this negative sign is significant because our observed sample mean was less than the claim in the null hypothesis. So what this is telling me is that a mean of 7.5 hours of sleep from a sample of 22 students, well, that's about 1.4-ish standard errors less than the value that was claimed in the null. Okay, and we've got a two-tailed test. So first thing here is that we're going to use a t-distribution. And we've got our degrees of freedom are going to be n minus 1. Since we had a sample of 22 students, we're going to use a t-distribution with 21 degrees of freedom. And so here's our kind of underlying distribution. Our observed sample was minus 1.38. So anything that is even further to the left of that would be extreme. And since this is a two-tailed test, we would also want to take into account anything that was that many standard errors above the claim in the null hypothesis. So this is a two-tailed test here. So one way that we can do this is calculate the area in one of these tails and then double it because t-distributions are symmetric. So here the p-value we can calculate by taking what's the probability that we would get a t-test statistic which is less than or equal to minus 1.38. And then double it to also take into account what's the probability that t is greater than or equal to positive 1.38. And so for this, we could use r, for example, and say we're going to calculate 2 times pt is going to give us the cumulative distribution for t-distribution. So we want to know how much area is to the left of minus 1.38 for a t-distribution. And here the parameter that we use to describe the t-distribution are the degrees of freedom. And we've got 21 degrees of freedom. And so calculating this in R gives us a value of 0.182. So that's our p-value. And I'll show you before we stop here, the last slide, is going to have a t-distribution table. So I'll just talk about how we could approximate the p-value from the t-distribution table. But here we've got a p-value of 0.182, and we want to know, is this therefore a significant result? And our p-value in this case, unfortunately, is big, certainly bigger than the significance level of 5%. So we failed to reject HO. And the test is inconclusive. And so if you were doing this calculation and you did not have R available to you, then it is possible to estimate the p-values using a t-distribution table. So that's what I want to just quickly highlight how you could do that on the next slide. And okay, so here's the t-distribution table. And so if we wanted to calculate the p-value, first of all, we had degrees of freedom here were n-1. Our sample size was 22, so we have 21 degrees of freedom. So that means we would want to look in this column over here. And in this row, we're going to look for our test statistic, which we found as minus 1.38. And so first thing to keep in mind is we've only got positive values over here. And my value falls between these two values over here. So I need to take my negative value and just take its absolute value of that, and then see between which two values in that row does it fall between. And 1.38 falls between 1.323, 1.729, 721. And then we look at, well, do we have a one or a two-tailed test? Over here, in this case, we were doing a two-tailed test. So these values over here are going to tell me what the p-value would be if I had a test statistic of exactly 1.323. And this is telling me this is what the p-value would be for a two-tailed test if that was your test statistic. And since our test statistic fell between those two values, then we know that the p-value for our test statistic is going to fall between the two values up in the two-tail row that we have up top. So our p-value is going to be bigger than 0.1, but less than 0.2, and that matches what we got from R, which said the p-value was about 0.18. So if you didn't have R available to you and you did have a t-distribution table, this is how we used to approximate them back in the day.